Hello and welcome. I'm Bill Wake. We're here working on the Elm interpreter written in Swift, and this is going to be our wrap-up episode. It's not like we finished it, but I don't know, 51 episodes in, I feel like that's enough time on it. We'll talk about how to wrap it up. I would say we've got about a third, maybe 40%, maybe a hair more done in the whole Elm interpreter. I'd like to think we got the hard stuff done, but I know we've got some things that would be a little challenging yet. And I don't know, the rate of it isn't detracting me. I'd like to try some shorter type things. So next week, starting Tuesday, I'm going to do a probably 1 to 3 episodes on the Towers of Hanoi and look at recursion and some ideas around how do you make it not recursive and things like that. So I think that'll be an interesting one, a little short algorithm kind of thing. But for today, we're going to start with go back to the IDE if I can get there. Here we go. All right, we have a test run going. So where we left off, last time we did a bunch of work around function calls, cleaning up how it handled errors, and we did a little bit of a defect fixing because function calls, if you had like 3.04, it would say, oh, that looks like a function call, and it would call it, and even though 3.0 is not a function. And we did a little bit on custom values. We put them in the symbol table rather than a separate table. So the idea is the system-defined objects like the operators and predefined functions and custom values and things like that. Those are all in the symbol table ready to look at while you're either compiling or interpreting. We want it while we're compiling because the type system uses those, and we definitely need it while we're interpreting because we need those values then to do the work. And we also have other values we'll put in a table as we go, as we interpret. So I think that's all right. Let's start a little. So today's the 29th, and this is episode 51. All right. We have a few things we've noticed. One's around, I'm not sure if this is a function call issue or a tuple issue. Lambda XX 3.0 gives float, but if you apply it to as the second argument of a tuple, it doesn't know what it's doing or something. And it sounds fixable. The type system stuff is one of the places where I'm disappointed. I really hoped I would find some information about how they do types, and it may be that like I should go look at Haskell because so much of Elm seems to be derived from Haskell and a couple other functional languages I've done a little bit of staring at. But on its own, it doesn't have enough semantics definition for me to know exactly what stuff means. However, having it return float one time and unknown the other is definitely suspicious. Let's see, what else can we do? Crashes, I don't really have much energy for that. I don't think it's going to be very interesting. Comparison operators, that might be a good one. We don't really have strings or arrays, so there's no point doing the append. That one could be a possibility, but I think this will be enough. We had some issues around the REPL, another type issue. That looks like just explanation. We have something around generic types. Yeah, that's a tricky one. Okay. Yeah, I think we'll focus here. And really my plan is I'd like to do maybe an hour of work on the existing ideas. And then kind of an hour reviewing the thoughts that went into doing this and the code we have so far. So take that how we go. All right, so comparison operators. Let's start with the REPL. All right, so we know less than it actually uses this comparable idea. And a comparable is sort of a generic type, but it's not as free as say generic, just the generic, normal generic. A comparable can only be certain things. It can be like ints, floats, I think strings, I think arrays, and I think tuples get done, an element at a time. But you can't just have an arbitrary type and it's comparable. I don't know if Boolean is comparable. Let's try that. False, less than true. Yeah, doesn't know. Okay, int, float, char, and string, lists and tuples of comparables. Okay. Now we don't have chars or strings or lists, so we just have to worry about ints and floats. And what I see with comparable is it's sort of another generic type. And so I think what we'd like to say is if you're comparable, I think we'll need to introduce a comparable type. And then when we do type checking and type kind of unification, we want to make int and float unify with comparable. So comparable. So if you do comparable plus an int, it should say, oh, you're really an int, and this is int to bool. Okay, I don't know if we can compare. This may do automatic conversions. Okay, it does, but we can't do this. Okay, they're not compatible. Okay, in this one it became number less than number. And okay, so let's try a hardcore int less than 4.0. Yeah. So when it was number here, 3 is a type number by default, which means I could be an int, I could be a float. You can use me either way, like JavaScript. Versus a float, it was fine. It says, okay, float and number, they're compatible, and we'll compare them. But when I force it to be an int, an actual int, not just a number, it says, oh wait, that's int versus float. That doesn't make sense. All right. So as often the case, we kind of have to decide what's. It helps if we do some work in advance, I guess, before we jump into the hardcore comparison. Let's see if. Well, let's run our REPL. That'll be a nice comparison. I think we have the operator defined. I think it probably is defined as generic goes to generic to bool. Well, it says he's running. All right. So we'll take the old less than operator and tell us what you are. Unknown. Okay. Let's find our primitive functions. Oh yeah, there's our list, and less than is not on it. Okay, so we have well, we somewhere down here we have these functions for them. Oh, well, most of them are operators, so it doesn't matter. Convert function numeric types. Well, we have a new concept that's like comparable. Let's see what this does. All right, so you give it an int function and a double function, and it's going to basically convert them, apply the function depending whether it should be int or float. So if they're both integers, it's an integer value. If either one is a float or both, it's a float. Otherwise, it's an error. So this is how do you build a function that compares ints or doubles. Now, we only have int and float, so we can kind of squeak through with this. If they're both ints, it takes int. If otherwise, it converts them to float and goes. So, yeah, we can take advantage of this. And I don't think that's any. I don't think it brings anything new. It's just putting it in. Well, no, it does. The only we have this comparable idea, and well, another interesting piece of this. Let's take less than 3. Okay, so this is really 3 is less than x, and it's going to be a function returning what? Number. Yeah, it's interesting. Okay. It knows that. Maybe we don't need to worry about comparable just yet. Like, I don't know how we could tell. We would like to find one behavior that's different because it's comparable or not comparable. I guess the difference we have is this is going to complain. Yeah. Okay. Right. So I guess if you give it, well, convert function. Let's go back there. We got a little different situation here. So if well, maybe we don't. The error could be better. It's not a cannot happen. It's really it's something about comparables, I guess. Maybe we should make our own. If it's int and int, they can compare. That's fine. I guess the real issue is if the type is not comparable, then, if this is a comparable function and the type is not comparable, then we got an issue. And we can certainly give a better message than this. The question to me is, I guess these don't care. All right, so we've probably got a test for this, right? Callers. Well, we're using it there. Let's see. I guess we're testing it with this. All right, let's imagine some tests. Int divide returns int. All right, let's say function test. Can we just ask if ints are comparable? I'm going to borrow this, but it's not what we want. Okay. Integer value 3. And then we're going to make this an explicit integer. Now I'll put the arguments down so we can see them. Okay, so we built up a function. If we say let result equal function of Oh, sorry. That's our arguments we want here. Integer value 3 and 4. The type here, we got to give it the function. And for now, let's just do less than. Well, yeah. Integer value. Okay. Oh, well, these are, let's convert relational. Function. Okay, we're going to give less than ints, less than doubles. We're going to talk about the case for integer. And if you evaluate this, well, it's actually about the same as this, except Boolean. Do we have a Boolean value somewhere up here? Yeah. Elm false, Elm true. Oh, 3 less than 4 should be Elm true. Okay. And its type should be Boolean, which is primitive functions bool type. Okay. So if you compare 3 less than 4, both integers, you expect to get a Boolean back, and we expect the value true. Okay. We don't have a convert relational type, but it's going to look an awful lot like this one. And I'll put it down there. Maybe down here. Okay, so int and a double function, and it returns expression. Yeah, except its type is going to be Boolean. All right. But it's returning, notice this complicated thing is saying I'm returning a function of 2 arguments that yields an expression, and we're returning a closure here. This little inside brace with x, y, n is the closure. So it's the function being returned, and then our curry method turns it into a function of 1 argument going to a function of 1 argument going to a value. I know it's kind of crazy. All right, so let's just return some junk, and I'll just return this thing for now. We're just gonna make things fail a little bit. Okay, now can I build? We're trying to get our test to fail. Oh. Double. Oh. I left a... Okay, he's not going to let me. Well, we should have no trouble failing both these assertions. Okay. All right. So we get this function. We want the result to be Boolean. It's not. It's error. Cool. All right. So let's peel off this first clause. And we'll move this one down. Okay, if it's an x, we're going to return an integer value. Int function. Well, now the int function returns a bool, so we need to convert it to the Elm domain. And I don't know if we have constants up here. False and true up there in the custom type, but we don't have actual constants. So let's add those. I think they're justified. Yeah, I think they're okay. We may have to construct them though. I don't think it'll let us reference the previous one like some languages do. Are you gonna complain? All right. Let's make this to Boolean. Swift bool to Elm bool. That's the guy we want. Oh, which means I probably don't need those. This is, I think it should be the same, right? Just return that. Swift bool to Elm bool. We don't need those values. Okay. If they're both integers, return swift bool to Elm bool of the integer function. Okay, let's try that. And I'm thinking this should be passing now. This is the only place that calls that function, so I'm not going to be too worried about it. I don't feel like I have to call everything. All right, it's trying. Okay, good. So let's do the same thing with number and float. Okay, so we'll take the same function, but this is going to be a float value with elm type dot float, and this will default to number. Okay, so we're going to compare. Well, let's make it a little different just to check that both sides are doing their job. All right, so we're going to say integer 13, float value 4. We think 13 less than 4 should be false, but it should be a Boolean. All right, and I probably could have just run the one file. Okay, but that will fail because it only gets down to here. And then I think we're going to, we'll have a situation that's different. This one is now cannot happen. Okay. I think we're going to want a different one that says something that could theoretically generate that message about the types aren't comparable. Let's see. Elm false. That failed as desired. All right, so I'm basically getting rid of this now. Well, it's there. Convert the left side, convert the right side, and then we're going to do the same little trick. We get a Boolean, we're going to convert it to an Elm Boolean. Let's take a look at that just to... Okay, yeah, it just turns into a custom value. All right, so Swift bool to Elm bool, and I think this will pass its test. Someday. All right. And now I want to do one that's... let's try booleans. Booleans are not comparable. And we should get a message. We must have had an example of that, right? Maybe not. Message. Some primitive numbers. A circular result. Yeah, okay, that's the kind of thing we're after. Booleans are not comparable. Okay, and then we want the assertion. Error message cannot happen. Well, I don't want... that's not quite what I want. Let's compare Elm false less than Elm true. And I think that can go on one line. Okay, convert less than false, less than true. And the error message we want is really types are not comparable. All right. Okay, I think that's a true enough thing. This test, did you really... And it should fail. It should get a cannot happen. Although I'm not sure the order of things. We may have to... Oh, they become nil if they don't convert to float. While that's running, I'm going to go try and see if something can fix. I'll be right there. All right, I had something running in the background I was able to kill off. I hope that helps some. But, okay, we got a failure. The failure should be wrong message. That's easily fixed. We'll just borrow this. Primitive functions, error messages, that. And then all tests should pass. Well, you can't quite tell, can you? Maybe this is just inherently slow. It seemed slow yesterday. All right, we'll let that run. I guess I want to look at primitive functions, kind of anticipate what's up next. So what we see here is to put it in the table, we're going to put it there with these three types, which says make the operator be number goes to number goes to number, or number goes integer goes to integer, or generic goes to Boolean for equals. We don't have a comparable yet, so our tables, we can just call it generic, and that'll get us forward. All right, but what we did was we added support for relational operator less than. Okay, but it's not yet in the operators table. So the parsing is there, but if we ran it, it's not in this list, so it's not going to show up as anything. But I think we can put it in place now. All right, so we want the less than operator, and our thing was convert relational function. Two functions passed in, less than and less than. And for now, let's just say it does generic bool type. I'm not inclined to test that my table is my table, so I'll run it manually. I don't know, maybe there is some deserving of a less than test somewhere along the way, but we hope we get A goes to bool, or Boolean. When we look up the value of the less than prefix operator. All right, if everything's good, this thing is defined. Right. And now we should be able to say less than, 3, 4 should be true. And less than 13, 4.0 should be false. Nice. I guess false should be an error. Pretty good. Okay. And let's look at let's look at 3 false. So a number versus a Boolean, same problem. Okay. Cool. That's good. Now I would like to the thing that's going on that isn't quite kosher is when we do less than 3 false, we parse that and we build up an expression tree, and as far as we know, everything looks good. Okay, you're calling less than with 3 and false. It wants generic. I throw in a 3, I throw in a false. Who cares? There's some issue around that too, but at any rate, it from a type checking perspective in our system, it says, it's generic. They're both generic. It fits. It's fine. Then when we go to the runtime part, it actually calls that function we just wrote, and then it gets this error, types are not comparable. But we should have gotten that error before we executed. I mean, you can't tell the execution. Yeah, let's try this. How about if true, then 3, else, I'm going to put it on less than. Let me put this in a full parenthesized, or mostly full. Okay, so if true, then 3, else less than 3, false. This should actually have a syntax error that says 3 and false are not comparable. My prediction is, and I'm gonna make one of these a 4 just so we can make sure we're telling things apart. My prediction is this will evaluate to 3 of type number. It does not. Okay. Oh, compatible type. That's interesting. Less than for false. I guess it does Boolean. Okay, let's try a different way. If we say if true, then false, else less than for false. Okay, I think this will come back false and not error. Yeah. Okay, so we can tell that in this case the if then else never evaluated the else clause because it came up true. So there was no error detected at evaluation time because it never executed that part of things. However, if we do this same thing on the REPL, I think we're going to see an error. I hope we're going to see one. Hope I'm not making this all up. Else less than 3 false. Yeah. Okay, so false is a bool, but less than needs a number. Okay, let's do a variation. Let's do false true or true false. I'd still like an error. Yeah. Okay. The true value is a bool, but less than needs a comparable. I don't know how to compare bool values. We said it a lot more succinctly. Beginners would probably prefer this. But again, I haven't evaluated it. I could evaluate it if I didn't type check it. False looks good. Less than, who cares? It's always going to return a Boolean anyway, so they're compatible. But, we don't do it that way. We actually do a sort of compile time checking. Compile is a little loose, but there's sort of the lexical analysis, the parsing we do, and then the semantic analysis, including the type checking, all happens before the interpretation. So it's clear to me the Elm REPL is doing that same kind of thing. Somehow it's processing it, checking the semantics, and then interpreting, so it doesn't evaluate this unless the semantics are all compatible. And that's one of the selling points, right? We get static type checking, fully type checked functional stuff, and rather than rely on the runtime. So our types are, they're explicit types. What am I trying to say? There's good phrasing for this in the literature that I'm not coming up with, but the types we have, like our values are strongly typed. They know they're a bool or an int or a float or anything like that. And at runtime, it detected the error because it can't compare a Boolean to an integer or a number. And because we have runtime, we have some runtime checking going on there. Elm, though, is supposed to be defined in a way that the type checking can be compile time, and we would never try to run that in the first place. So it's static, strictly typed, I guess you'd say. And without that rule, our case, it's at least partly dynamically strictly checked. Okay. Yeah, so I think this is probably a good time for a break. I think what we'll do when we get back, let's introduce this comparable type. So this thing is really comparable to Boolean. And I think if we do that, we would see the error before it happened, before runtime. All right, so just a couple, 3 minutes at most. All right, see you in a bit. Hey, welcome back. All right, so what we'd like to do then is introduce some sort of comparable type And I think we can, I think if we just introduce it, we will see the consequences of it. And Elm type doesn't have a comparable yet. Okay, we're just going to add it. Generic, it's closer to generic than anything, I think, so we'll add it here. All right, so all I've done is say there is a type. Oh, shoot. I didn't push, did I? All right, let me comment this out and change this back. Okay. Yeah, I definitely want to. Okay. Do a clean in a build. Just little weird bugs with Xcode once in a while. I mean, it's a challenging job. I mean, as a language, Swift is pretty big, right? It's well, this is getting annoying now. Elm type. Dot generic. Okay. Will you please? Okay, I think he's happy. Pretty bad when it doesn't even take care of it on a clean. All right, but we replace generic with the word generic and all appears well. At any rate, looking forward, I would like to introduce the comparable term in the Elm types and use it for this operator. At some point, somebody's going to try and say, are you compatible with this operator? And be like, I don't know, and probably get an error. Okay, so commit this. Add less than to primitive operators table. All right, now I'm going to change it back to what I had. Comparable. I don't know why this lined up that way, but they appear to have. Elm type has no member comparable. Okay. Now let's see what happens. All right. Yeah. Okay. We have to do something. I guess I don't mind. I don't want to get down into the weeds of too far down, I guess. Description of a comparable type. Okay. Again, I still anticipate something failing. If we can't make it fail, I don't know, we'll put a test in for some of this. I'm not liking these parentheses around error there. That could be a quick change too. All right. Yeah, so, interesting. No impact yet. Somehow, let's see, where do we compare types? Joint type. Yeah, so nobody tries any Elm type level comparison of types. So this is actually, let me see. Let's run the REPL. I think we may already have an error, and we can reveal it if we do. My hope is I've broken something. We'll see. That should be legal, and it is. Okay. Wow. I mean, comparable. Okay, let's try. Less than 3. Just give it one argument. Comparable to bool. Okay. Well, that's nice enough. Okay. So, okay, let's do our if true thing. If true, then false, else less than false, true. Must have compatible type. Yeah, so that's a different error than we saw before. All right, so I guess even this. See, this error is still coming from our runtime. That should be a compile time error. All right. I know it's kind of an arbitrary distinction in some ways, but it's kind of the point of Elm is the static typing approach is that in theory, you could get rid of all the type checks at runtime because everything is type checked at compile time. And so you wouldn't have to have, like I have in the interpreter now, if it's 2 ints, then do this. And if it's, true and false, do that. All that stuff could be tossed away, and you would just always be working with exactly the right types. We're not as sophisticated as that in what we do, but this is definitely an error, and this is definitely an error, but the error should be coming out sooner. All right, so less than false true. Let's see where we can make an example of that. Well, it's really a function call because we convert those prefix operators are just function calls. But that's all done before we get there. Well, where's that going to be then? Is it a parsing issue? And maybe it is. All right, so when you got expressions here and you wrap a function call, let's see what goes on there. All right, so if the left argument is function or generic, we allow it. I don't know where, what I'm after is this joint type thing. Who references that? Apply. Oh, check joint type. Well, really what we want. Okay, I guess I should just say what I want here. What I want is check joint type with comparable. Oh, well, I guess I can make a check. Let's go down here. Generic plus other. I guess that's a check joint type. Okay. Let's take this. Okay, the joint type of an integer. Well, let's make this a comparable. Joint type of comparable and float should be float. Okay, so the expected is Elm type dot float. All right, and I'll just run this. And I'm expecting it to fail. Still, here we go. Error is not equal to float. Okay, so that is the failing test for this. Error is not equal to float. I don't know why it's in there twice. But Elm type. Okay, if you're comparing generic to comparable, you should get comparable, so that part's there. But I think we want to say this: if self is comparable, well, if we're comparing a comparable to, we only have specific types, and how about other dot is comparable, then other. Okay, we've only got one side so far, and I don't have a method for that, but let's add it. Private function is comparable, returns a bool. Okay. So if, I guess, self equals float, will pass. I don't know if I need to do all the combinations, but okay. So if we got a comparable with a comparable type, I guess comparable and comparable is legal too. But this test only checks float, so let's just go this far. Okay, go back here. And we already have a check that if they're equal, so comparable already works. This should pass. I don't know why I get so insulted, but when you tell me it's 1.3 seconds and it takes about 20, it really gets me. Okay, so much for my theory. Error is not equal to float. Comparable and float. All right, so I came through. I wasn't error. I wasn't other. I wasn't generic. I was comparable. My other is comparable. If I'm float, return a. I don't see the problem. All right, and let me break here. Comparable float should be float. Comparable and other, return other. That seems okay to me. As always, speak up if you see it. Oh, I think I checked both ways. That's why it's two assertions. Yes. All right. Let's add the other side. Well, it's going to run now. My helpful check method. Let's just stop that. All right, we'll do the other side. Whoops. If other equals comparable and self is comparable, return self. Okay. And I'm going to add my next test. Well, let's just run this one. I think I'll extend this test. I don't know. I maybe should put my effort back into that parameterized test thing I had going. Okay. So let's check type of comparable and any numeric type should be numeric. We'll say it that way. Okay, and I'm really just checking the three combinations I most care about: float, int, and number. Speed things up a little here. Okay, should fail the last two. Oh, come on. Integer. What's your problem? Cannot find number. Okay, 1551 should fail. Okay. Gets error. All right. Now my comparable method. Just take that breakpoint out. Let's return self is float, or self is integer, or self is number. All right. Okay, so we've introduced comparable type and checked its joint type with numeric types. All right, let's run it. My hope is when we run less than false true, we get a slightly different message, but still a correct message about type compatibility. And if it's okay, I will leave it be. I wonder if this is the 14.5 simulator. It just came out the other day. I wonder if there's something slow about it or what's going on here. All right, less than false true. Should complain. We're still getting down there. Okay. I mean, it's not wrong, but it's not where I wanted it to complain. All right, so let's find that joint type thing again. Who uses that? And maybe it's not being used at compile time and apply or if statement. Well, apply, that's the actual function call. Well, it's saying if I apply this function to this type, what do I get for a return type? Let's try another one. Let's try less than false. Comparable to bool. Yeah, that's still not quite what we want. Joint type is not error. Return it. Okay, and the other one was if statement. Again, I think that's a little weird of a place to be enforcing this. Evaluate joint. Oh, parser. Okay. well, this requires the two branches of the if to be the same. Okay, let's see that one. If true, then false, else less than false, true. That might work. No, yeah. Yeah, that's actually correct. These two have different types. It's checking that before we run it rather than running it and not realizing it. Okay, I'm happy then. Now, at a function call, I would have thought that could catch it there, but I'm going to let that go. The thing I would like to change, and I don't know, this may not affect tests, or it might. There's probably a few, but I'm just forcing a new name. Error type is not really a defined Elm kind of thing, as far as I can tell. It's something done in the approach I'm using here that I just enforce that things have a type when there's errors, and they appear not to care about it, which is fine. And I want to do the same thing for unknown. Probably put these more together and those more together. Okay, yeah, it's more of a, we check that people return .error, but I think the description only shows up when you actually run the interpreter. Again, this one may also have no errors. I don't typically worry about the strings too much. Maybe I should worry more, but I don't. We could have made assertions there, but I have fewer assertions at the interpreter level, and maybe that's the cost of setting up a big integration test kind of thing. Okay, so change type description for error Elm type dot error and unknown. Just a little, I don't know, polish. Let's see. Well, I would like to add my other primitive functions, so let's do that. And I don't feel compelled to do a lot of direct testing here either. I don't know. Maybe I should be more diligent on this too. But we got less than or equal, greater, and greater or equal. Okay, and the operators less than or equal. Greater, whoops. Greater equal and greater equal. We need the two separate ones because one's integers, one's doubles. Okay, less than or equal, greater, equal, greater, equal. Okay. And my hope is this just works. Yeah, some of these that are more like a configuration thing, I don't know, sometimes it's just as easy to visually examine the table and see if you approve of it. Typing it in doesn't necessarily give you any more confidence. Let's say less than or equal 5 less than or equal to 5. True. Less than or equal 5, 5.0. I assume this is true. All right. Can we say 3 less than 5? Less or equal to 5? We didn't really check those infix operators before, but they seem to be good. 5 greater than 2. 5 greater than 5. False, yes. Less or equal, less than, we need a greater than equal. 5 greater or equal to 5. And 5 greater or equal to 5.1. Okay. I'm good. All right. I'm happy with that. Let's sketch that over here. Comparison operators in fix. This can go down. And then I think our next task is I would just like to kind of review what we have. And, well, normally we wait a few more minutes for a break, but let's take a break now. We'll come back, and the rest of the time we'll just kind of look at the design, look at what I think works and doesn't work, and go from there. So let's see, all tested, run. Well, our manual tests, I should say. Maybe I should run all tests too. All right, but anyway, let's take that quick break, 2 or 3 minutes. Come back, and we'll walk through things from a design level with some pictures and then the code level, see what we got. Welcome back. All right, let's see. So we will pick up from the picture side. All right, we did that. All right, so I started this project, I don't know, sometime after the start of the year, right? So 51 is 17 weeks. So that's 4 months. That's basically April. So, take this into the end of April, and that's about where we are. So what I expected, I thought, well, Elm's bigger than Lisp for sure, and it's smaller than C. It shouldn't be too bad to parse it and get all the interpreter going. I don't know if you've ever seen the Lisp interpreter, but it's written on about 3-4 pages in Lisp, and if you implement it pretty directly, you get a Lisp interpreter in not too much time. You might have to do a little work to make your lists and maybe some supporting atomic kind of things, but you just need a handful of primitives, and once you have that, it falls out really quick. I don't know if I could do it in 2 hours. That'd be a nice goal, but it's pretty quick. And I thought, oh, well, Elm will be similar. Yeah, it's a little more complicated, but it shouldn't be too bad. Well, yeah. Another thing I wanted to do was try out parser combinators, and we went down that path a fair bit. What got me stuck, or what I didn't like, was you had this kind of backtracking approach where you would run multiple parsers in parallel, and then some of them would drop out, and then if everything dropped out, you had a good parse kind of thing. Or you can work them sequentially. If I try this, if that doesn't work, try that, and so on. And then you got to worry about, did I try the longest one first, and stuff like that. It's an interesting concept. I don't think it worked terribly well in Swift. I needed to create more mechanism than I was kind of willing to do. So yeah, I balked. And what we did instead was basically recursive descent, which if you've got a grammar that's written for it, is really a trivial way to go. We'll talk about that in the code, but it's a really easy way to go. So it's not a very pretty way to go with a moderately large language, but it's easy. Okay. Then I expected we have a small grammar, and we do. It's smallish. I mean, smaller than C is kind of my borderline there. But you need a lot of look ahead, not from a textual parsing point of view, but from the point of view of the semantics we're trying to apply. So my canonical case for that is, if you have a function definition, it looks like function X, Y, Z, A, B, C, D, E. You can keep going as long as you want, this long string of identifiers. And up until you either see an equals or end of file, you don't know whether you're calling an existing function or redefining it. or defining it. And so you have an arbitrarily deep parse, and then you got to decide, oh, I see an equals. Now I realize I wish those were all variables because this is a definition. And the contrast might be like if I had, say, a let keyword in front of it, so my evaluation looked like function XYZ, but my definition looked like let function of XYZ equals something, some indicator to let me know what I was doing. I don't have that in Elm. There's a few places that are kind of tricky that way. The other place that was a little hard is the way operators work. Now, my understanding is older versions of Elm lets you redefine operators and define your own operators and things like that with your own precedence and associativity. We took the precedence and associativity from the system definitions. So the rule now is the system definitions are allowed to do this, but users aren't. But still, it's like 9, 10 levels, something like that. And some are associative to the right and some to the left and some not at all. And with that kind of thing going on, that would be very awkward in recursive descent. You actually would have to have at least one method for each level and a little trickiness around when it's associative or not. And you end up having to really pay attention to understand what it's doing and stuff like that. So I wasn't happy to have to do that. So we switched gears and mixed parsers, and we mixed in an expression parser. And the expression parser takes a table of operators with their precedence associativity and does the right thing. So that was easier to do than the recursive descent 11 levels, and it let us try a little different grammar approach. All right. I expected clear semantics because it's functional, and people have been thinking about the semantics of functional languages forever, but I just could not find a lot of explanation for the Elm stuff. Everything I found was pretty informal, and the type checking stuff in particular, we were just in joint type. I don't know if we've got that right or not. I try and take plausible guesses based on what I've seen in other languages, but that's not it's not a way to run a railroad, I guess, in some sense. I mean, Elm's young. It's not like every language has their semantics on day one or anything like that. But I thought, oh, it will be there, and maybe I need to go dig up Haskell semantics and pretend it's Haskell where they overlap in capability. And I doubt they've strayed too far from that. I mean, that's kind of the family they're in. I expected it'll be fun. Well, I've had fun with it. It's, I allow myself to whine some, but it's interesting and fun for me. So hopefully it was for any of you that are around. All right. So the structure or the design overview, on the left, you've got the input coming from the REPL, our user interface, and that's characters going in. And then the lexical analysis produces a stream of tokens, and tokens are just sort of composed characters. So rather than feeding the name A, B, C, D, E, here's a string of alphabetic letters, and then the parser has to accumulate them, and the parser has to worry about, is this a space or a new line, and are they equivalent, and what if there's a comment, and all that stuff. Lexical analysis does that, so the Lexer does that for us. Then we get into the parsing side, and this is all kind of compiler-ish. The main parser we talked about, recursive descent, so things like if and definitions and stuff like that are done in the main parser. And for expressions, the main parser just gathers them. So that was the operator operator expression, expressions, and expression. A lot of overlap in terminology there, but that's the three main methods that the parser uses to pull out, identify a stream of stuff that forms an expression. So it's been syntax checked by the main parser, and then we're using the expression parser to form the tree. So if you have 3 plus 4 times 5, 4 times 5 should get precedence and be structured to evaluate first. If you have 4 times 5 plus 3, the 4 times 5 should be first. If it's 3 plus 4 plus 7, the 3 plus 4 should be first, and so on. The various combinations of associativity and precedence, and the The expression parser basically takes in a list of expressions that have been verified to be in a legitimate overall expression, and then it applies the precedence operators and produces a new expression that basically puts the operators as function calls. That was those prefix operators with the parentheses, turns them into those kind of function calls, and it looks like a bunch of function calls at that point. I think that's a winning move, the bunch of function calls. Just like when we do a definition, we turn it into a bunch of lambda expressions. I think that's a good move in terms of the semantics. We're moving to a more primitive kind of thing. Then we get to the interpreter side. The interpreter is built around these expression trees. So all the lexicon parsing was done to produce an expression tree. And it's got an evaluate method that takes a symbol table and produces an expression. So the reality is some expressions are sort of like the concrete values, like integers and floats and booleans. And other expressions are more function calls and lambdas and whatever else. Now the symbol table we use, basically the operators are in there. The Boolean types are in there. Those are the system things we have now. When you go to evaluate things, if you have a lambda expression, lambda n goes to n plus 3, then we create a new symbol table with the n, and when you evaluate n plus 3, you use the new symbol table. All right, so when evaluation of the expression is done, we should have a concrete expression like an integer, a float, in the long run, strings or arrays and whatever else. We print that out to a string of characters, and then that's what's put in the REPL. So the read eval print, that's the print part. It takes the expression you get back and turns it into characters and puts it in the UI. All right. Let's look at expression a little more deeply. So this is the tree. The whole point of the parser is to build up an expression tree. So if you have a function call less than 3, 4, then you have a function call node. The function is less than. The argument is integer value 3, and then the other argument is integer value 4. So that's that green arrow on top there that says expressions may contain other expressions. And so the function call at the top has 2 nodes, well, 3 nodes beneath it, the function, the argument, the expression. And actually in our case, like function less than 3, 4, the less than is actually a variable. And so the function there is variable. Name is parentheses less than parentheses. Even if you said 3 less than 4, it turns it into that. And when you evaluate it, you can only find the value of a name by looking it up somewhere, and that's the purpose of the symbol table. So if you want to find out what is the less than function, you have the string parentheses less than parentheses. You look it up in the symbol table. It says, oh, it's the curried function of a relational function type of less than less than. That's all kind of Swift language that we just looked at. But that function is wrapped up. The curry wraps it up into a function that we can hand back to the runtime. And so it's holding on to that. It looks up the symbol table, gets the function, gets the arguments, evaluates them, and then applies the function to the arguments. And that's the job of the function call. Integer value is one of these concrete types. It's simple. It just returns itself. If integer, float, they just evaluate to themselves. Same for Boolean and so on. And then there are a bunch of nodes. We'll look at some of them. But the evaluate is basically, it's a tree walker, and it chooses which pieces of the tree to do. So there's an if node. It's got a condition. It's got a left and a right. And the evaluate is evaluate the condition. If it's true, go to the left. Return the value of the left. If it's false, return the value on the right. And, again, the evaluates are usually reasonably simple. All right. And then finally, the symbol table. Maybe I should have shown a set of them, but basically a symbol table has an outer symbol table. It's really optional. So pointing back to itself, or it has a dictionary, we called it the inner, which takes names and turns them into expressions. So let's take lambda n goes to n less than 3. All right. So the the outermost symbol table we have, well, it's going to have a nil child, nil outer. It's the end of the line, and it defines less than, equals, plus, all those operators and the booleans. That's our outermost symbol table. Then when we do the lambda, we create a new symbol table object. Its outer points to the system one, and its dictionary is going to have n is going to map to n less than 3. All right. And then the evaluation, in the evaluation process, we're going to look things up. We look to look up a name. So we're looking up n less than 3. We've done the n. Now we're looking up the less. We say if the dictionary contains less, all right, return it. Okay, but it doesn't, because we have the outermost dictionary contains n. If not, try it in the outer table. Okay, so it either looks in the symbol table for the lambda. If it can't find it there, it goes to the next one, which could be the outermost system one, or we could have lambda n goes, lambda x goes to lambda y goes to lambda z goes to some expression. We'd have a stack of tables. Each one has its own thing. And if we reference some variable that's not in our local scope, we'd be looking in some outer scope to try and find it. And so the nesting of the symbol table reflects absolutely the nesting of the evaluation and the nesting of the text. All right. So what we're going to do is we'll just walk through the pieces. I'm going to start with the lexer. Well, let's start with input. Okay. So input is really us keeping track of the string coming in. And so we have this notion of a location, line number, and column. So our error reporting, like in line 1, column 4, you messed up the types. Okay. Well, here's the description. That's actually the English out of it. But our input is basically an array of characters. So when you input a string, we split it up into the array of characters, and then you can ask for the next character. The lexical analysis is going to ask for the next character, and it'll get the character and the location. All right. So that lets us keep track of the errors and report the locations. Otherwise, it's doing a little bit of work to skip. It keeps track of where the new lines are, so it can reset the column number and stuff like that. But not much there. And then it can look one character in advance if it needs to. Okay. And if you get too far, it just hard locks onto input into file. All right. I think that one's that's pretty short and sweet. Now the lexical analysis, basically every kind of thing, every entity from a textual point of view gets broken up into its own token. And so we define tokens for things. Error is, how we catch errors at this level, end of file, new line. But then it gets interesting, ints and floats. Okay, so if you've got 3 or 37 or 42 by themselves, no decimal points, it says, oh, that's an integer. 42.7, oh, it must be a float. And then lowercase names, A, B, C, D, or uppercase names. Reserved words, we only have if, then, else so far. Parentheses, operators. And at one point we had each one separate, plus, minus, times, and we folded them in together to one operator type. I think when we switched to the operator precedence, it just was easier to deal with it wrapped up as one thing. Okay. Some other operators we kind of have custom meaning for, lambda and arrow and so on. This may not be used. Let's see. Oh, less than bar, greater. Yeah, those are actually function operators. If we proceeded on to do all that stuff, we would probably move those into operator as well. I don't know. We'd have to see what the syntax is. All right. So the token. Let's get to the main place. Okay. Here's reserved words. Here's the token you'll get, and so on. So you set it up, you give it the input, and it's gonna use the input. You give it a string, it's gonna turn it into a bunch of characters. We have this notion that we prime the pump. So priming the pump says when you're gonna parse strings or something, it's really helpful to know the next character without having done anything about it. You just kind of want to peek at it. And if you always leave that ready to go when you're coming back around for a new token, you always leave it so that the next character is the first one available. And that convention just makes things flow very easily. We do the same thing in the parser, you'll see later. So we initialize it, we prime the pump here, we set a starting location. And then the whole function of this thing, the focus, is get. And get is, remember we said we turn it into a stream of tokens? Well, that's get in action. We don't actually turn it into like a full stream that you then read the stream. We could, but we actually do it more on demand. You call get and get a token back. It's okay either way. All right, so the token process, this is actually, tokens are defined as regular expressions usually. So you can have you have basic elements like letters and digits and numbers and whatever those things are, the kinds of characters, operator plus and so on. Or you can do alternation with the or bar, so I can say if or else or then or something. Or I have repetition with the star, and I can say repeat this. So I could say an integer is defined to be 0 through 9 plus. Plus is a variation that says one or more of things. But you could simulate it by 0 or 9, 0 to 9 star, and have the same thing. So you have a regular expression, and we know regular expressions and finite state machines are equivalent. So this is sort of a variation of the two. It's kind of a code-oriented implementation of a finite state machine, I would call it. All right, so what we're going to do is we're saying, all I'm doing is looking at the first token and I'm making a decision about what's going on. All right. Except there's there are a couple cases, but one goofy case is if you see a space, we're just going to skip spaces. So let's go down and look at that. All right. And he just says, while you have spaces, skip while. Okay. And we have a few helper things down on the bottom here. Let's find skip while. Well, there's keep while if I want to keep these things in a token, and there's keep and skip until and skip while. So, basically skip until you find some terminator, skip while you match a character. Okay. So, very, very commonly used, but spaces, we skip them. Notice there's no return like there is for the others. If we see a bunch of spaces, we're just going to skip forward, and then we'll exit the bottom of this case statement or switch statement somewhere. Okay, we get here, then we're going to go back around to the top of this loop, which I think I can click and it'll take me there. So basically, keep reading. If you find spaces, skip them until you get to something that's not spaces or end of file, and if you hit the end of file, you're done. All right, and then for most of this, there are a lot of things that are single character tokens. So if I see a right parenthesis or a backslash, I know exactly what kind of token it is. All right. You are a right parenthesis token. You're a lambda token. You're a comma token. Various operators and so on. Okay. Now here's all the we also have two token characters. Okay, 2 character tokens. If you have dot and it's followed by another dot, then your token dot dot dot. If you didn't see another dot after it, you just saw a dot like a dot b, you're a token dot dot. Same thing for this, plus and plus plus, less, and if it's equals, less than or equal, if it's less than this, if it's bar. So most of these things are either 1 character or 2 character tokens. We'll hit the exceptions. So if you got digits, you're going to start a string of digits, possibly followed by a dot and more digits. We're not going to call that a dot token in the middle. We're going to say it's just one big floating point token. If it starts with A to Z capitals, it's uppercase name, lowercase name. All right, so each of these has a method. And, basically, if you've got an uppercase name, you're going to keep any letters A through Z, 0 through 9, or underscore. you have to do that dot 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 because the way sets of ranges do. But in any case, you're basically just gathering characters that match that thing. So here's the A to Z, and here's the A to Z star. It all boils down to one of these and zero or more of these. We already know we have a capital A through Z, so we can just jump in and kind of pretend it allows everything. But we gather these, same thing for the lowercase name. We just gather them. And lowercase names, we got to look up and make sure it could be a reserved word like if, then, or else. And if it is, then we're going to return the map we had above. Otherwise, it's just a lowercase name and you return it. Okay. And let's find numbers. They're more complicated. All right. Yeah, here's numbers. And if you write out the regular expression for it, you definitely can see it's like is 0 or 9, one or more of those. So digits. It could be dot digits after that, or it could be E plus or minus digits. So you can say 3.7 E plus 2, and that's a legal float. All right. And so each of these pieces, if all you have is this piece in front, you have an integer. If you have this piece and this piece or both, you have a float. All right. So we're going to gather the digits while we got them. Then if we see a dot, we know it's a float, and we'll keep the dot and gather more digits. Okay. If we see an E, upper or lower, again, we know it's got to be a float, and it may have a plus or minus, so we can consume those. And it must have more digits, so we'll check for that. And at the end, we've either got a float, if it had those two possibilities, or it's still just those digits at the front and it's an integer. It's ugly enough. I mean, I don't know. This is 400 lines, maybe 384 lines. You know, you can see why people like parser generators to do this work. All right. And then let me hit, well, there are two other complicated cases. Let's touch on those. One is this left brace, and it's actually more complicated even than it shows here, but we only support left braces with a dash, anything inside, and it ends with a dash brace, but they're nestable comments. So this is not a regular expression. This is jumping into a recursive thing. And you can see here, nestable comment is called by nestable comment. So if you see a brace dash inside a brace dash, it's like you need to do a whole parse of the nestable comment. It might have more nesting comments and stuff. So it definitely introduces some complexity here. I mean, it's all very straightforward, following the state machine and everything, but you know, it adds up. And then let's find the parend. Whoops. Left parend, return left parenthesis. Okay, this method. All right, so this method, the complication here is you might have left parenthesis followed by operators, like we've been doing today, less than, parenthesis less than, right parenthesis. Okay, so it could be one of those. It could be just a normal parenthesized expression, you know, 3 plus parentheses 4 times 5. Or maybe 3 plus 4, all in parentheses, times 5, you know, to do the grouping like you learned in grade school probably. Or it could be a tuple. Okay, so we don't know what it is. You know, basically we have to work it out along the way. So if we see a bunch of operators, then we assume it's an operator set. If not, you know, we're looking at something that's more like a tuple. We're just going to return the left parenthesis and let the parser work it all out. Okay, so this is all pretty straightforward coding. It gets overwhelming in bulk, I believe, but that's where it is. All right, let's touch the parser. All right, so recursive descent, this parser is doing that. Basically, we got a bunch of setup. We'll come back. But the notion is you have grammar rules. Let's get down to one. Here's function call or definition. goes to expressions or possibly followed by equals expressions. So that's function xy equals x plus y would be a definition, a function call, or I'm sorry, a definition. If it was just function xy, then it's a function call. So we're basically gathering the operator expression that corresponds there, and waiting to decide what to do. Okay, so we aren't quite sure. In function definition, if it's a function definition, these have to be a bunch of variables on the left-hand side. All right, and so we'll enforce that. Let's see. So we pre-declare function to return lambda expression from function prototype. I think this one is probably enforcing it. Okay, yeah. So function prototype variables, if they have a problem, they return an error. Okay, so the function prototype variables, we look at those. We say, okay, they really are all variables. We're going to pretend there's a function defined like this, and we don't know what the definition is yet, but we're gonna kind of rely on that. We have to do that to allow recursion, because if function xy equals blah 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 function something something, if we just looked it up at that moment by default, function doesn't exist. We haven't finished defining it. So this wrap function type and all that stuff is there to basically force a fake prototype, well, a real prototype, into the symbol table, so we can do the evaluation. All right. And then the rest of these, we just did these the other day, so I'm not going to spend any time on them, but they're enforcing semantics. So basically you have the recursive descent does this stuff where expression plus operators and more expressions 0 or more times, but expressions 1 or more times. This grammar rule turns into code, check for operator. If you have it, grab it, get the next expressions. It's in a loop that corresponds to the star. All that stuff is parsing. And then somewhere down here, we do, we call the post order method, that the post order class that deals with how do I interpret an expression. So this is the point where it's switching over to the precedence parser. But, the recursive descent point of view, we just translate names of rules into function calls on the rules, and operators plus star parentheses, we translate them into loops and stuff like that. Alternation, A or B kind of things, we have an if statement of some sort, and then the rest becomes semantics. All right. And I don't think there's anything terribly interesting going on in that sense. Like, you've got a rule and you can just check, here's an alternation. We have a switch statement on the token. If it's an int token, go to int. If it's a float token, go to float, and so on. Each one does its own deal. All right. Parenthesized expression. I'll cover this as kind of part 2 of the tuple stuff. So you get a bunch of expressions, and then you may have comma expressions. Okay, that's what makes it a tuple. We've already ruled out that it's not an operator, prefix operator with parenthesis less than parenthesis. And it may or may not be a simple expression. It could be a tuple or a simple expression. So we parse the operator expressions. We're gathering them up into results and parsing them again. So this is, here's the comma. So parse expressions, look for a comma. If there is one, then do this. And you can do this 1 or more times. Braces are sort of like saying a plus. Maybe I should just change it to plus for consistency. But you get tangled in the meta language of plus and times and the language you're parsing. It's easy to get mixed up. But at any rate, you gather all this stuff into a bunch of expression lists broken up by commas. We're going to do wrap tuple. And basically, wrap tuple does the work. It says if there's only one, then it must have been a regular old parenthesis like you learned in grade school. If there's 2 or 3, we're going to build a tuple, an Elm type tuple. And if there's 4 or more, Elm doesn't allow that anymore. So you can't have a tuple with 4 elements in it, and we return an error. Okay, so I think for the most part, this is all, the parser is a very straightforward-ish transliteration of the grammar into code. You have to do some work on the grammar to make it compatible with it, but it's not terribly hard to do that. Similar to the Lexer, it just allows the recursion. All right, and then let's get to our precedence parser. So this is the case of, 3 plus 4 times 5. There's just an algorithm I literally took from the Dragon book of compilers of how do you do a relational or precedence parser. And basically you build a big table of operators. This one's less than that one, this one's equal to that one, and so on. And you've got an algorithm that says look up the top of the stack. You're maintaining a stack of sort of partially looked at operators, and you got the operator on the current input. You're going to compare them, and either you're going to push the new operator on the stack, or you're going to say, oh, we should actually evaluate things, and you're going to start popping things off the stack. And when you do that, you basically get what they call the postfix of the expression. So 3 plus 4, if you think the node is plus in the middle and 3 and 4 are the leaves, it's going to do the left child, the right child, and the center. So 3 plus 4 is plus 3, 4. I guess I should do it the other way. 3, 4 plus is the postfix of that. And if it was 3 plus 4 times 5, it would be 3, 4, 5 times plus. Okay. And given that they're in that order and you know how many arguments they take, you can easily take that and generate a tree back from it. And that's what we do is convert it back into a tree that we evaluate. All right. And then, so finally, let me go to expressions. So I guess we'll look at symbol table real quick because that's the easy one. I think it reflects basically what we saw with the outer table that corresponds to an outer scope, and the inner table corresponds to the current scope. Every name maps to an expression, and to look it up, you either look it up in the inner or the outer, or else it's null. And a similar thing for the types. Okay, we use that to evaluate expressions. So here's the parent type, and the parent says, you don't implement me. I'm just the placeholder for things. So I hold the type, but everything else I tell you you should be doing the work. Okay. But the core of it is evaluate. And that's the one we'll focus on. Evaluate says, give me the symbol table and the expression I am, and I'll turn it into a new expression. And we'll take float value. We mentioned it already. Evaluate is just self, right? You should expect int value to be the same thing. Evaluate is self, okay? Because if you evaluate 4, you get 4, and that's a potential answer for the whole thing. All right, we have custom values. They might be a little, they're the same. So if you get false or true, it just is what it is. All right, let's get an interesting one. I think function call is probably the most interesting here. This one's moderately complex, okay, but we're holding on to a list of expressions that's basically the function and its arguments. Okay, so we will, back to evaluate, we're going to take the first thing, which is the function, and evaluate it in the context. So if it was a less than operator, we would look it up and have this function there. Then we'll drop the first thing because it's the function. And then this is where we do the partial application. So Elm curries functions. So if you have a function of 2 arguments, it basically you evaluate the function with the first argument, you apply it. That will give you a function of 1 argument back, and you evaluate it again and apply it. But you can stop. You could say parenthesis less than 3, like we did it before. And that returns a function from number to Boolean. All right. And this is where that happens. If you kind of run out of closures, run out of function definitions, you're done. You ran out of arguments basically, and stop applying it. Okay. If you run out of arguments first, well, if you get down and you get something that's not a function, then you can't evaluate that. 3.0 applied to 4. But if you have a function that's a closure and you ran out of arguments, that's fine. You just return the closure, which is the semi-evaluated function. And let's peek at that. And I think I've done this right, but I'm not 100% sure. It's where I wish we had more explicit semantics. But basically, I'm saying a closure captures a symbol table, and this is kind of a read-only thing to it. And it captures a functional expression, the lambda expression, and it's prepared to evaluate that. Okay, so, apply is the real core of it. And apply says take the lambda and apply it with the symbol table, and that's where you'll get the value of it. All right, and let's take, is there another one that's moderately different? Well, if is probably interesting. Okay, so you evaluate the condition with the symbol table. So if A is less than B, then you take the result, and if it's a Boolean and it's true, you evaluate the left side and return that. Otherwise, you evaluate the right side and return that, and you cast it to the type that's the joint type of both of them. All right. And so that's really it from the expression side. Every expression node has an evaluation. You just crank through them, evaluating until you run out of stuff and you're down to concrete things like 3 or 4 or a list. And that's good. And then we have the interpreter. He's read eval print. Well, here's the read is you give me a string. It parses it, gets an expression, and then evaluates the expression with a symbol table. All right, which has our prefix operator stuff in it. All right, and then print is just evaluate it and print its description. So that's pretty well it. Okay, and there's some helper stuff and all that we didn't go into, but we've got a fair bit. A couple hundred tests. We got over 203. Got to 203 today. All right. So I don't know. I hope this has been interesting. We definitely had a dive into several topics around, especially around parsing and semantics and all that stuff. It's close-ish. I mean, I don't know. There's probably some stuff that's interpreted wrong by me, but it evaluates some simple expressions, and we did the recursive factorial the other day. All right. So thanks for coming along the journey for this one. I'm still going to have the same hours going forward, but I'm just going to do kind of, I think, try and stick to a week at most on a topic, just to kind of try more stuff. All right. And I'm going to start next time with Towers of Hanoi and look at recursive functions, use that to look at recursive functions, memoization, which is an optimization, and converting it to iterative. So both those will be interesting for us, I think. And that is Tuesday, 1 to 3 p.m. Eastern time. So thanks again. Take care, and I hope to catch you in the future. Bye-bye.